Say you've got a list of numbers, all jumbled up, and you need it sorted, smallest to largest. With 8 numbers? Sure, you could eyeball it. But what about 1,000,000? Now you need a real method, something fast. Here's an idea. What if you just split the list in half, and split those halves again into smaller and smaller pieces? Then comes the clever part, joining them back together, and joining 2 piles that are already sorted. That turns out to be surprisingly easy. Split it down, then merge it back. That's the idea behind MERGESORT. But how does that actually work? Let's find out. Sorting 8 messy numbers feels hard, so let's not. The trick behind MERGESORT: don't solve the big problem, break it in half. Take the list, cut it down the middle. 2 halves, still too big. Cut each half again, and again, until every piece is a single number. And a single number is already sorted. Nothing to do. But splitting didn't sort anything, so here's the real question. How do we put the pieces back together, in order? This is the whole secret. Merging 2 sorted lists is easy. Look only at the front of each. Compare just those 2. Take the smaller one, place it down, repeat. 2 sorted lists become 1 sorted list in a single pass. So we climb back up. Singles merge into sorted pairs. Pairs merge into sorted 4s. 4s merge into the whole list, now fully sorted. Split all the way down, merge all the way up. That's divide and conquer. Break it down until it's trivial, then combine the easy answers into the full answer. And merging sorted lists, that easy step is what makes MERGESORT fast. Let's read it line by line. Low and high are just the start and end positions. MERGESORT, AR, low, high. Line 1, if low is greater than or equal to high, return. This is our stop sign, already sorted, so we stop. Mid, we find the middle, the place we cut. Then the magic. The function calls itself, once on the left, once on the right. And last, merge, we zip those 2 sorted halves back together. Now here's the zipper itself. We make an empty list, temp. 2 pointers, I on left, J on right. We compare the 2, take the smaller into temp, and slide forward. When one pile runs out, dump leftovers, then copy temp back. We start with the whole array, low 0 to high 7, 6, 5, 3, 1, 8, 7, 2, 4. We split at the middle into left and right. We dive all the way down the left first. 6, 5 splits into 6 and 5. Merge them, 5 is smaller, so we get 5, 6. Then 3, 1 gives 1, 3. Merge those 2 sorted pairs, and the whole left half becomes 1, 3, 5, 6. Same on the right. 8, 7 becomes 7, 8, 2, 4 becomes 2, 4, merged into 2, 4, 7, 8. Now the grand finale, the big zipper. Our 2 sorted halves, watch every comparison. Left is 1, right is 2, take 1. Now left 3, right 2, take 2. Left 3, right 4, take 3. Left 5, right 4, take 4. Left 5, right 7, take 5. Left 6, right 7, take 6. And now the left pile is empty. So we just dump the leftovers, 7, then 8, straight on the end. And look at that, perfectly sorted. And notice, every single step was just one tiny comparison. The dividing made the merge effortless. Let's build the merge, one line at a time. We pass indices, not copies. The left half is low to mid, the right is mid plus 1 talus to high. Temp is our new sorted list. I and J are 2 scanners, and they only ever move forward. While both halves have cards, take the smaller and advance only the pointer that won. And notice the less than or equal. On a tie, we take the left first. That's a stable sort. When one half runs out, just dump the leftovers. No comparing, they're already sorted. And copy temp back into the array, skip this, and nothing actually changes. Every card is touched once, so the merge is ON. Clean, fast, and stable. Last question, how good is it? Picture the whole thing as a tree. 2 questions, how tall is it and how much work per level? How tall? We keep halving until we hit 1. For 8 elements, 8, 4, 2, 1, That's 3 cuts, which is log base 2 of 8. A logarithm is just how many times do I halve to reach one? 1,000,000 items, only about 20 levels. Halving is powerful, so the height is log n. Now, work per level. At every level, the merging touches all the elements once, so each level costs about n work. Multiply them, n work times log n levels equals O of n log n. And here's what's special. We never peek at the data to decide what to do. We always cut in half, always merge. So it's O of n log n in the best, average, and worst case. It never has a bad day. But nothing's free. To zip the halves, we needed that temp array, extra memory. At the top, that's room for all n elements. So merge sort needs O of n extra space. Quicksort sorts in place with almost no extra memory, but it can have a slow worst case. Merge sort spends memory to buy a rock-solid guarantee. That's the trade-off, so that's merge sort. Divide on the way down, merge on the way up. Thanks for thinking it through with me. See you next time.